Welcome to the NPTEL MOOC on Discrete Mathematics. This is the 7th lecture on mathematical logic. In the last class, we were talking about a proof system for first order logic. The proof system consists of a set of logical axioms. We saw 6 templates for forming logical axioms. 3 of them were identical to the logical axioms of the first order logic, the propositional calculus, and then we had 3 additional logical axioms for first order logic. So these form the logical axioms of first order logic. And then we have one rule of inference. Exactly as in the case of propositional calculus, the rule of inference that we have is modus ponens, which says that if we have alpha and alpha implies beta, then we can prove beta. What this means is that given a set of formulae gamma, which will form the set of proper axioms, we have a system like this. We have the logical axioms and we have the rule of inference modus ponens, and we have a set of proper axioms gamma. So here gamma is rather a plugin. You can change the set of proper axioms that you have. When you change gamma, the conclusions would change. Then with this system, with gamma, the logical axioms and modus ponens, you can write what are called proofs. A proof is a sequence of statements or well-formed formulae, so that the first statement of the proof is an axiom. This could be either a logical axiom or a proper axiom, and the subsequent statements are either axioms or obtainable from the previous statements by modus ponens. But of course, since modus ponens should have 2 formulae to be applicable, we know that beta 2 also is an axiom. So in any proof, the first 2 statements are axioms, the remaining statements are all axioms or obtainable by modus ponens. That is, we are visualizing sequences of this sort. Beta 1, beta 2 are axioms. Any beta I is either an axiom or is obtained by some beta j, and beta k which is beta j implies beta I. These 2 together will provide beta I. So every statement is obtainable in this manner. Such a sequence of well-formed formulae is called a proof. Any statement in a proof, any well-formed formula, so that a proof ends in it, is a theorem. So if beta 1 through beta n is a proof, then all of these statements, beta 1 through beta n, are theorems. That is because you can stop the proof at any point. Beta 1 is a proof, beta 1, beta 2 is a proof, beta 1, beta 2, beta 3 is a proof. In other words, any prefix of this sequence is a proof. Therefore, the statements at which these proofs culminate are all theorems. that is beta 1, beta 2, beta 3, etc., beta n are all theorems. Every statement in a proof is a theorem, but usually we attach the word theorem to a significant conclusion, but in the case of logic that is not the case. Any statement in a proof is a theorem. Then we spoke about models. An interpretation context pair which is what breathes life into the syntactic system that we have laid out. An interpretation context pair is a model for the set of proper axioms gamma if gamma is true in that pair. In other words, every well-formed formula in gamma is true under that interpretation context pair. In that case, we say that this interpretation context pair is a model for gamma. Then the question is this: given gamma and given the models for gamma, which statements are true, which statements or well-formed formulae are true in all of these models? These are exactly the logical consequences of gamma. What is the logical consequence of a formula? Beta is a logical consequence of alpha if beta is true whenever alpha is true. That is, any interpretation context pair which makes alpha true will also make beta true. That is when we say that beta is a logical consequence of alpha. Now, when we are given a set of formulae gamma, we say that beta is a logical consequence of gamma if any interpretation context pair which makes every single statement of gamma true will also make alpha true. So, that is precisely what we are saying here. A model for gamma is an interpretation context pair which will make every statement of gamma true. If such a model will also make a statement alpha true, if every such model will also make a statement alpha true, then we say alpha is a logical consequence of gamma. Notationally, we write in this manner: alpha is a logical consequence of gamma. Now, the question is, given alpha, how do we check this? This is where the proof system comes handy. When the proof system furnishes us with a proof, where the proof culminates with alpha, we would say that alpha is provable from gamma. That is, using gamma and the logical axioms, we are capable of proving alpha. Now, we would like this to be identical to this. That is, the semantic notion of logical consequence and the syntactic notion of provability. You know, proving is a strictly syntactic process. We are merely looking at the forms of the statements and rewriting them. So, a proof is a strictly syntactic process. Using the syntactic process, we are arriving at alpha. Here, logical consequence is a semantic notion. We want the syntactic notion of provability and the semantic notion of logical consequence to be equal. That is when we say that the proof system is sound and complete. Okay, now let us consider one concrete example for proper axioms. Let us consider a system of logic in which there is one predicate symbol, which is the equality symbol, and then there are function symbols, there is one constant symbol or a 0 argument function symbol, which is z, and there is a one variable function symbol, which is s. There are two variable function symbols, which are a and m. Let us say these are the only symbols that the system has, the function symbols and the predicate symbols. So these, along with the logical connectives, quantifiers, brackets, will form the alphabet of the language, and the set gamma consists of the following axioms. Axiom S1 is this: it is essentially a statement about equality. It is about the transitivity of equality. What it says is that for every x1, x2 and x3, if x1 equal to x2 and x1 equal to x3, then x2 is equal to x3. We will use this as a short form for this. So whenever I write like this, you should understand that this is what I mean. The second axiom is also about equality. The second axiom is about the S function. S function can be thought of as the successor function. We would call it the successor function. So what it says is that for every x1 and x2, if x1 is equal to x2, then the successor of x1 is the same as the successor of x2, which means every number has a unique successor. And then we say that z is not the successor of anyone. That is what the third axiom is. And the fourth axiom asserts for every x1 and x2, if the successor of x1 and the successor of x2 are the same, then x1 and x2 are the same. This is the converse of the second axiom. Then the fifth axiom asserts that for every x1, apply A on x1 and z, we get x1. The fifth axiom asserts that for every x1, A applied on x and z will give us x1. The sixth axiom says that x1, x2, for every x1, x2, A of x1 and the successor of x2 is the same as the successor of A of x1 and x2. Now probably you can guess where we are headed. What is the meaning of A? In the seventh axiom, we assert that for every x1, the m function applied on x1 and z will give us z. The eighth axiom says that for every x1 and x2, m on x1 and the successor of x2 is the same as A applied on m on x1, x2 and x1. And the final axiom S9 is in fact an axiom schema. It says that for any well-formed formula alpha with one free variable x, alpha of 0 implies that for all x or alpha of z, implies that for all x, alpha of x implies alpha of successor of x implies for all x alpha of x. So, let us say gamma is this set of proper axioms. Now, we have written gamma with an intention of interpreting them in a particular way. For example, we would like to interpret z as 0, we would like to interpret a as the addition function and m as the multiplication function, and the successor function is the plus 1 function, in the sense that the successor of 7 is 8. Let us take another look at the axioms with this interpretation in mind. So, the first axiom says that equality is transitive. The second axiom says that for every x1 and x2, if x1 equal to x2, then s of x1 equal to s of x2, or in other words, if x1 equal to x2, then x1 plus 1 is the same as x2 plus 1. The third axiom says that 0 is not the successor of anyone, and the fourth axiom says that if x1 and x2 have the same successor, then x1 equal to x2. In other words, if x1 plus 1 equal to x2 plus 2, then you can cancel 1 from both sides and get x1 equal to x2. The fifth axiom says that when 0 is added to x1, we get x1. That is, 0 is the identity of addition. In the sixth axiom, we say that x1 added to the successor of x2, that is x1 plus x2 plus 1, is the same as x1 plus x2 plus 1. So, from this you can essentially derive the associativity of addition. In the seventh axiom, we have multiplication with 0. We know that 0 of multiplication, that is x1 into z, is z. In the eighth axiom, we have distributivity. x1 multiplied by x2 plus 1 is the same as x1 x2 plus x1. So, from this we can derive the general form of distributivity. And the ninth axiom is in fact the principle of induction. For any well-formed formula alpha of x, if you can show that alpha is true for 0, and also that for any x, if alpha is true for x, then alpha is true for x plus 1. If both of these can be shown, then we can argue that alpha is true for every x. So, this is the principle of induction. So, all these axioms put together form our set gamma. So, gamma is called Peano's axioms. And forms the basis for theory of natural numbers. So, we can think of an interpretation I naught, D naught, F naught and R naught, where D naught is the set of natural numbers, F naught maps the function symbols, it maps z to 0, a to the addition function, m to the multiplication function, and the one variable successor function to the increment function plus 1. So, that is what F naught does. R naught maps the equality symbol to the identity function, the identity relation, which consists of pairs of the form XX. So, this way we interpret all the symbols, function symbols and predicate symbols of the language. So, this interpretation is called the standard model. For our first order system S. S is the first order system with Peano's axioms. as the proper axioms. That is, when within the proof system we plug in gamma, the system of Peano's axioms, what we get is the first order system of S. This interpretation, where D naught is defined as the set of all natural numbers and F naught and R naught are defined in this fashion, is called the standard model for S. In fact, any interpretation which is equinumerous with this interpretation is also called a standard model. But let us don't bother about equinumerosity at this point in time. So this is what we will call a standard model for S. We call this a model because we can check that every one of S1 through S8 and instances of S9 are true in this interpretation. That is why we say that I naught is a model for S. So that is an example of a first order proof system with a concrete gamma. Now let us go back to the original question. We have a question of this form. We are given gamma and we are given an alpha. We want to answer this question really. This is what we are interested in. Is alpha a logical consequence of gamma? We have designed a proof system to essentially answer this question. And what we want is this. Is there any relationship between the provability of alpha from gamma and the logical consequence of alpha being a logical consequence of gamma? Is there any relation between the two? We would like these two notions to be identical. In other words, we would like the system to be sound if the system is sound, then anything that we prove is sound. In other words, anything that we prove is a logical consequence. So if there exists a proof culminating in alpha within this system, where any of these statements is either an axiom or follows from two of the previous statements by modus ponens, then alpha is provable, and then we would like to argue that alpha is a logical consequence of gamma. So this is when we would say that the system is sound. It can indeed be shown that the proof system consisting of logical axioms and modus ponens is sound, in the sense that you use any plug-in gamma, anything that is provable within this system would be a logical consequence of gamma. So the system that we have been discussing is sound. The other question is the completeness. We would like to know that the system is complete. In other words, we would like to know that if alpha is a logical consequence of gamma, then alpha is provable. Gödel's famous completeness theorem proves just this. It shows that this proof system is indeed complete. That is, when you use a proof system of this sort with axiom schemas A1 through A6 as the logical axioms and modus ponens as the rewriting rule, then every logical consequence happens to be provable. So the proof system is sound and complete. But there are some remaining questions. Consider the standard model I naught for Peano system. This is just one interpretation, and in this one interpretation, suppose this rectangle represents the set of all well-formed formulae or syntactically correct formulae. So let us say I naught makes some of these formulae true. In particular, it will also make all of gamma true. Consider another interpretation which will make some other set of formulae true. Of course, these two sets of formulae may overlap. Suppose I1 is also a model for gamma, that is, gamma is true under this interpretation I1 as well. Now imagine a third interpretation which will make yet another set of formulae true. Suppose this is also a model for gamma. So in this sense, let me imagine all models for gamma. There could be countably infinite number of models for gamma. Then the intersection of all of these will form the logical consequences of gamma. That is because these statements, the shaded portion within the Venn diagram, when we have plugged in all imaginable interpretations, we find that the intersection of all of them is exactly the logical consequences of gamma. So in all these interpretations, gamma is true, therefore all of them are models for gamma, and in all these interpretations, these shaded portion is also true. Therefore, we can say that any interpretation which makes the whole of gamma true will also make all these formulae true. So these are the logical consequences of gamma, and these are indeed the statements which are provable within our system. So the shaded portion is what is provable within the system. Now let us consider I naught. We are going back to I naught. We find that the shaded portion is a subset of I naught. Now, what is the circle I naught? It is supposedly the set of all statements that are true in the standard interpretation, and the shaded portion is the set of all statements that are true in every interpretation that will make gamma true. Of course, I naught also makes gamma true, but there could be more statements which are true in I naught. Or in other words, the statements that are true in I naught and the set of logical consequences of gamma need not be the same. They need not form the same set. Or in other words, there could be a statement that is true in I naught, which is not a logical consequence of gamma. Clearly, the second set is a subset of the first, but what I am saying is that the two sets need not be equal. The second set could be a proper subset of the first set, in which case there would be a statement in I naught which is not a logical consequence of gamma. The famous Gödel's incompleteness theorem establishes just this. This statement shows that there is a well-formed formula that is true in I naught but is not a logical consequence of gamma, where gamma is the set of Peano's axioms and so is not provable from gamma. That is because by the soundness and completeness of the first order system, where we obtain completeness from Gödel's completeness theorem, what we know is that logical consequences of gamma are exactly the statements that are provable from gamma. Therefore, if there is a statement that is true in I naught which is not a logical consequence of gamma, then this statement will not be provable from gamma. But then what is the significance of I naught? I naught is the standard interpretation. It interprets the domain of discourse as a set of natural numbers, and the function symbols and the predicate symbols in a familiar way. We have the zero symbol and the addition symbol and multiplication symbol and the successor symbol, and when you read the axioms in this sense, you realize that it is the set of axioms for the theory of natural numbers. Therefore, there is a statement which is true according to our intuitive understanding of numbers, which is not provable from gamma. The demonstration of such a statement formed Gödel's incompleteness theorem. Gödel's construction was roughly like this. For every syntactic entity, we can define a unique number. This is a way of encoding the syntactic entity. For example, we can assign a symbol, a number for the opening bracket, let us say 13. For the closing bracket, we can assign a number 17, and so on. And then combining these, we can assign a number, we can find a way of encoding every syntactic entity into a number. For example, when I have a statement of this form, the corresponding number for this could be the number corresponding to the opening bracket multiplied by the number corresponding to A1 multiplied by the number corresponding to implication, and so on. This is one way of encoding, and this encoding has the property that we can uniquely decode any such given number. So Gödel demonstrated that such an encoding is possible for the syntactic entities. These are called Gödel numbering. Once the syntactic entities are encoded into numbers, you can treat numbers as syntactic entities. And then when you look at the statements within the system, we find that we have well-formed formulae with free variables. In particular, if I look at a well-formed formula alpha with one free variable x, it seems to be saying something about x. The statement could be something like this: x plus 1 equal to 5. So this is a formula with one free variable x. By substituting for x, I can get various formulae. Some of them are true, some of them are false, and so on. So those are formulae with one free variables. But then formulae with one free variables now can also be thought of as speaking about syntactic entities, because now we have mapped syntactic entities into numbers in a one-to-one manner. Therefore, at least some of the numbers represent valid syntactic entities. So a formula with one free variable can be thought of as talking about a particular number, but a number can be thought of as a syntactic entity as well. So now we have formulae talking about syntactic entities. But what are syntactic entities? The symbols are syntactic entities, the function symbols, predicate symbols, open close brackets, implication, negation, all these are syntactic entities. And then well-formed formulae are syntactic entities, terms are syntactic entities which form constituents of well-formed formulae, and we can also consider proofs as syntactic entities. A proof is nothing but a sequence of formulae. So if you combine the Gödel numbers of the well-formed formulae belonging to a proof in an appropriate manner, we can also devise a Gödel number for a proof. So proofs are also syntactic entities. Now Gödel numbering maps all of these into the set of natural numbers in a one-to-one manner. Therefore, we can now have statements that are talking about syntactic entities, which include symbols, well-formed formulae, terms, proofs, etc. Therefore, we can have statements that are talking about provability. Roughly, when you have a statement which says that for every x, y is not proved by x. In other words, for every x, x is not a proof of y, is essentially asserting that y is not provable. Now, this statement itself has a Gödel number, and y is a free variable in that. So, by appropriate substitutions, we could devise an expression which essentially says that I am not provable. This is what Gödel did in his incompleteness theorem. He devised a formula which essentially says I am not provable. The meaning of the formula is I am not provable when you consider the standard interpretation of natural numbers. That is, from the perspective of our understanding of natural numbers, the formula can be thought of as meaning this. The formula is a self-referential formula, it refers to itself. It says that there is no y which is a proof of this statement. That is, the statement of the Gödel number inverse of which is this formula itself. But then, what would be the truth value of such a formula? Will this be provable? If this formula is provable, then by the soundness we know that it is a logical consequence, and therefore it is true. If this formula is provable, then it is true. But then what does the formula say? It asserts that there is no proof of this formula itself. Then there is no proof, or in other words, the formula is not provable. Which is a contradiction. If this formula is provable, then it is false, but it cannot be false because anything that is provable has to be true by the soundness of the system. Therefore, we have a contradiction. Therefore, it is not possible for this formula to be false. Therefore, in the standard interpretation, this formula is true, which means this formula is not provable. In other words, this formula is not a logical consequence of Peano's axioms. In other words, there is a formula which is true in the standard interpretation but is not a logical consequence of Peano's axioms. Or in other words, there is a statement which is true in the standard interpretation. According to our intuitive understanding of numbers, this formula has to be true, but it cannot be provable from the set of Peano's axioms. In other words, the proof system that we have laid out is not complete in that sense. That is, it is not capable of proving every statement which is true in the standard interpretation. It is capable of proving exactly the logical consequences of Peano's axioms. So, Gödel demonstrated that there exists a formula which is true according to our intuitive understanding of numbers and is not provable from Peano's axioms. Okay. So, this is the end of the discussion on mathematical logic and the end of this lecture. Hope to see you in the other modules. Thank you.